Hello, Honors Trig Pre-Calc, and we are looking at 2.7 and 2.8, solving equations and inequalities in one variable. So the first question I have for you is, what is an extraneous solution? That's probably something you've heard before, and maybe you remember, but an extraneous solution is a, I'm going to say quote unquote, solution we find when solving that does not actually make the equation true. So this often happens when we do things like we divide, well, we don't want to divide by 0, right? Do not want to divide by 0. And so often when we do problems that we're solving equations, we want to double check our answers to make sure there are no extraneous solutions. So we're going to do 3 kind of brief examples. The first one is very, very simple, right? Almost too simple to even kind of consider. 0 is equal to 4x minus 8. We add 8 to the other side, divide both sides by 4. X is equal to 2. Now this is the one and only solution. It's not extraneous, right? We can check our work by plugging it back in. 4 times 2 minus 8, 8 minus 8 is 0, and we are happy and good, right? As simple as can be. Let's look at a slightly more challenging example, but we're still going to be fine. X plus 2 is equal to 15 over x. So here's our second one. X plus 2 is equal to 15 over x. One way we could solve this is by multiplying both sides by x. And when we do that, we would get x squared plus 2x is equal to 15. Moving the 15 over, x squared plus 2x minus 15 is equal to 0. We see we have a quadratic, and hopefully your mind is like, yes, I want to factor that. I want to factor it into x plus 5, x minus 3 is equal to 0. Set each of the factors equal to 0, and we get x is equal to negative 5 and positive 3. Now, how do I know if either of my solutions would be extraneous? Well, I check my work. And you can truly check it completely, right? 3 plus 2 is 5. 15 divided by 3 is 5. Is 5 equal to 5? Yes, so 3 works. If we take negative 5 plus 2 is a negative 3. 15 divided by negative 5 is a negative 3. Those both work. We don't have any extraneous solutions here. What about something that's a little bit more complicated? Oops, like this guy. So we have x plus 2 over x minus 4 over x minus 1 plus 2 over x squared minus 1. What if we had something like this? Now there's actually 2 ways we can do this problem, and the first would be to graph it. Set one equation as y equals 0 in your calculator, and then set another equation as y equals this whole thing. And then we would be looking for where my functions intersect. And I'm mentioning this, even though we're not going to do it right now, because it's really good practice to kind of know how to do a problem more than one way. But if we want to look at this equation algebraically, not graphically, we need to get a common denominator. So x plus 2 over x minus 4 over x minus 1 plus 2 over x squared minus x. Notice for each of these, technically equals 0, we want to get to this as our common denominator. So this first fraction is missing an x minus 1, and the second fraction is missing an x. So I'm going to get that common denominator. All right, extend page. There we go. Get that common denominator. And I would write these as, I'm going to FOIL the numerator. So x squared plus 2x minus x minus 2 over x squared minus x minus 4x over x squared minus x plus 2 over x squared minus x is equal to 0. So notice I just multiplied these pieces here. We can continue by adding the numerators. So we would get x squared plus x, I'm adding these two together, minus 2 minus 4x plus 2 all over x squared minus x is equal to 0. I can simplify a little bit more, right? X squared minus 3x all over x squared minus x is equal to 0. Now, how do we solve this? Well, we can multiply both sides by this x squared minus x squared minus x. And notice that's going to cancel, right? So we're left with x squared minus 3x is equal to 0. We can factor this. X minus 3 is equal to 0 and solve. X is equal to 0 or 3. And now let's check these two solutions. Where was our original equation? Hold on, give me one moment. So if we look at our solutions, x equals 0 and x equals 3, and we plug them back in, notice we're going to have an issue. If I plug in 0 here, I would get 2 over 0. Can we divide by 0? No. This is an extraneous solution here because it does not actually make our equation true. It's a solution that came because of the way we solved and isn't actually a solution. So extraneous and wouldn't actually make it true. If we plug in 3, we're going to be fine, and I'm not going to work through that one, but it still makes 3 would make them all true. A small thing in this section that I want to remind us of is our limit notation, right? As the limit as x approaches a of a function is equal to L. What would this look like in our graphs? Well, we've seen it a couple times, but let's say that's 2, and let's say our function looks like this. Here's our function. So I could say the limit as x approaches infinity of our function, as x is getting really big, what's my y doing? This is equal to 2. We've seen this before, but it's just a reminder of our limit notation. And then let's talk about section 2.8. So 2.8 is honestly the same idea as 2.7, but we just add into it that we're not just doing this on equations with an equal side, but with inequalities. So what is a polynomial inequality? It's when we have a function that's either less than 0, a function that's greater than 0, a function that's less than or equal to 0, or a function that's greater than or equal to 0, right? These inequality symbols, where f of x is a polynomial. So this could look like x to the 7th plus 3x squared minus 1 is greater than or equal to 0. That's an example of a polynomial inequality. In this section, we are going to use sign charts to determine whether a function is positive, negative, or 0. And we've actually done this before, so we're going to work through this example in class, but I'm going to give you a couple reminders. The first thing we do here is to find the zeros. And once you have those zeros, you place the zeros on a number line. And then remember, we are going to pick a value in between those zeros to see if the function is positive in that range or negative in that range. Remember, it looks something like this, where we maybe have -1 and 2, and then we plug in 0 and we see, oh, the function is positive. We plug in 3, we see the function is negative. We plug in -2, we see the function is negative. This example that I just did is totally made up. This green thing right here, it does not necessarily work with the function over here. I guess I used I use totally different numbers. So this is just like to remind you of what that looks like. So we're going to use sign charts to solve our polynomial inequalities, and then we're going to answer the question of, well, where is it positive? Where is it negative? Where is it equal to 0? We will do some examples like this in class, and the only other thing I want to point out is if we have a rational function, right, a ratio of these polynomials, we not only need to use the zeros, but also our vertical asymptotes, because those are going to be places where the function breaks as well. So we're going to look at these examples in class, but I wanted to give you that tiny bit of information beforehand. If you have any questions with this video, let me know. Otherwise, have a great rest of your day.